Good morning, good afternoon, and good evening to all of you who are currently watching to this video. And first of all, I would like to introduce myself. My name is Zhuo, metric number A17KM0062. I am from School of Mechanical Engineering, University Technology, Malaysia. And before I start, I would like to express my gratitude towards the panels for spending your time to evaluate my work, and especially to my supervisor, Dr. Wan Famin, for guiding me in completing this undergraduate project 1 throughout the semester. So let's begin with my title, Cooling Slope Effects on Microstructure and Mechanical Properties of AZ91D Magnesium Alloy by Semi-Solid Processing. So what is AZ91D Magnesium Alloy? The 9 here stands for 9% of aluminum and the 1 here stands for 1% of zinc. D is for cadmium in ASTM specification B275. It has unique mechanical and mechanical properties which make it commonly used as a biomaterial. And as we all know, casting defects will reduce its mechanical properties, and by using semi-solid metal processing, it will combine the advantages of both liquid metal casting and solid metal forging process. So cooling slope casting is one of the most popular semi-solid metal processing due to its simplicity and cost-friendly. We do not have to purchase any extra expensive professional machineries to perform a cooling slope casting. And cooling slope parameters such as cooling slope angle, cooling slope length, and pouring temperature plays an important role on the microstructure and mechanical properties. And conventional casting has reached a plateau in materials engineering. Metal dendrites is one of the main reasons that causing brittle fracture. And cooling slope casting can produce semi-solid metal with higher strength and castability by a finer and uniform grains. The objectives of this project is to investigate the effect of cooling slope parameters on mechanical properties and microstructure properties of S-cast magnesium alloys, and also to investigate the solidification mechanism and growth rate kinetics with respect to the cooling slope parameters. The scope of this project includes to review the effect of cooling slope on microstructure changes and mechanical properties of alloys, to investigate the effect of cooling slope system with various melting temperature, angle of slope, and pouring distance, microstructural investigation of S-cast sample from the top, middle, and bottom of the slope, and the mold using an optical microscope to correlate solidification mechanism and growth rate kinetics, SEM and elemental verification using EDX. Investigate the mechanical properties of S-cast sample using tensile and viscous hardness machines. And next is literature review. This is a paper from 2019. Figure 1 shows the schematic diagram of a cooling slope setup. In this experiment, the slope angle is fixed at 60 degrees and the pouring temperature varies from 640, 650, and 660 degrees Celsius, and the slope length varies from 300, 400, and 500 millimeters. After conducting microstructure analysis, these two equations are used to find the shape factor and average grain size. For your information, when shape factor equals to 1, it means a perfect circle. So we are trying to approach 1 as much as possible. And this is the graphical result of this experiment, the optical micrographs. And after mechanical testing, we find that the real cast metal will have higher real strength, higher your ultimate tensile strength, and better elongation. And next paper is from 2018. Figure 1 shows the structure evolution in real casting from dendrite structure to become globular structure. Before flow dendrite, after flow forming of globular structure. And this is the microstructure of a semi-solid cast, and this is a microstructure of conventionally cast. So from figure 4, we can obviously see that the ultimate tensile strength, yield strength, and elongation of semi-solid metal is much better compared to the conventionally cast. And figure 5 shows the effect of shape factor on the ultimate tensile strength and elongation. We can see when the shape factor approach to 1, the ultimate strength and elongation are the highest. And this figure 6 shows the breaking of dendrite arms to form globular structure. And from the first paper, there's an optimum condition to produce the best microstructure and mechanical properties for semi-solid alloy. For this experiment, the best cooling slope length is 400 millimeters and the best pouring temperature is 650 degrees Celsius. The next paper shows that the ultimate tensile strength and elongation improves as the shape factor approach 1, and not only due to the non-dendritic microstructure, but also due to the small size of primary alpha aluminum. This is the mechanism of the forming of globules. Under a shear force, the dendrite arms bend plastically, and the dendrite arms experience large misorientation and form dislocation. These dendrite fragments act as nuclei, containing and leading to presence of globules of the primary phase. And this paper is from 2015. Table 3 shows the shape factor of top of slope, middle of slope, and bottom of slope. Shape factor closest to 1 is at bottom of the slope. And table 4 shows the shape factor at different pouring temperature. So closest to 1 is at pouring temperature 640 degrees Celsius. Table 5 varies slope length and also pouring temperature. The shape factor closest to 1 is at here and here. And table 6 varies the slope temperature and the pouring temperature. Shape factor closest to 1 is at here. And here is the summary for the paper on the effect of pouring temperature, slope length, and slope temperature. When the pouring temperature is too high, the nuclei might dissolve back into the melt, hindering nucleation. And when the slope length is long, the duration of contact between the molten metal and cooling slope increase, which might account for a large number formation of nuclei. And the temperature of molten metal tends to reduce further along the cooling slope, resulting in higher shear force and might account for a large number of nuclei. And increasing in slope temperature decreases cooling ability of the slope, reduce the chilling effect and resulting in low number of formation of nuclei. And the molten at the end of slope might remain at a high temperature, formed nuclei tends to dissolve back into the fluid and low number of nuclei will form. This paper from 2015 shows the behavior of Az91D magnesium alloy in human body. Results show that Az91D magnesium alloy will dissolve in human body. So when a temporary implantation is needed, Az91D can be used so that a second operation does not require to remove the temporary implantation. And in this paper, the pouring temperature varies, cooling slope angle varies, and the cooling slope length also varies. Note that the shape factor equation on this paper is same as the first paper. And this is the graphical result. The paper from 2015 shows that the Az91D magnesium alloy possesses a fatigue strength of 17 megapascal in modified simulated body fluid, which is considerably lower than required. This might due to the casting defect and indicating the need to use semi-solid processing method to enhance the material properties. And from the 2014 papers, the optimum condition to produce the semi-solid metal is at 660 degrees Celsius for temperature, cooling length 360 millimeters, slope angle 48 degree, and isothermal holding time is 9 minutes. And this is the experimental setup. And in this experiment, the slope angle is fixed at 60 degree, and the pouring temperature varies from 925, 940, and 960 Kelvin. And this experiment 1, 2, 3, and 4 each has its own casting parameters. The optimum casting figures will be discussed later in the literature comment section. This paper from 2012 shows that the 60-degree slope angle produces a sample with degree of sphericity as known as the shape factor closer to 1 and smaller grain size. From the optical micrographs, we can see the formation of globular structure throughout the cooling slope. And STM micrographs can be used to observe surface structure and flaws. So from the experiment, the best processing condition is 60 degrees slope angle, 925 Kelvin pouring temperature, and 333 Kelvin slope wall temperature. And similar to the first paper, the perimeter and surface area of alpha aluminium are used to calculate the shape factor and grain size of the sample. Similar equations are used in both papers. And in fact, these two equations to obtain the shape factor and average grain size are used in the most of the paper I had reviewed, usually with the aid of ImageJ software to obtain the required parameters, which are the area and perimeter of the globular structure. These three figures shows the change of microstructure after a certain process, and this is the change in shape factor after isothermal holding time. And this is the degeneration of the dendrite structure, growth of rosette, and turn into nearly globular grains. And this paper is to compare between light microscopy analysis and electron backscatter diffraction analysis. The paper from 2007 shows cooling stroke process will degenerate dendritic structure and finally form globular structure. Undergoing isothermal holding afterwards will improve the shape factor and make it become more globular. And paper from 2015 shows EBSD has much higher resolution compared to the optical microscopy technique. It will have a higher accuracy. However, the sample preparation stage is very crucial. And from the papers that I had reviewed to investigate the microstructure of semi-solid metal, all of them are using optical microscopy instead of EBSD, indicating optical microscopy should be sufficient to determine the grain size and globularity. And this is paper from 2002, and these are the difference between die-cast AZ91D and semi-solid cast AZ91D. And table 5 shows the corrosion rate of semi-solid process. AZ91D has much lower corrosion rate compared to die-cast AZ91D and pure magnesium, as well as table 6. And XRD allowed the identification of two distinct solid solutions, the primary and that constituting the rounded grains. And XRD pattern evidence the presence of these two solid solutions by a slight shift of the peaks at higher theta values. And now is methodology. This is the general physical properties of AZ91D magnesium alloy that I obtained from the JMAT Pro software. And this is the cooling stroke process I have designed using these parameters, and after that undergoes microstructure investigation and mechanical strength test. And this is the sample preparation for microstructure investigation, and after optical micrographs are examined, these two equations will be used to obtain the shape factor and also the average grain size. And this is to perform mechanical strength tests. And here is the expected outcome. Different experimental parameters will produce different microstructure in terms of globularity and grain size. And I predict that 640 degrees Celsius pouring temperature, 45 degrees slope angle, and 400 millimeter cooling length will produce a Z91D magnesium alloy with the best mechanical properties. This is the reference and the Gantt chart I have planned to conduct UGP1 and UGP2. Okay, that is all from me. Thank you very much.